Hello, dear friends. This is the continuation of mechanical vibration lecture. It is lecture 6. It is about forced vibration of single degree of freedom system. I will continue from the lecture where we stood in last September. In our previous lecture, we have seen the free vibration case. Different case of free vibration. So now we are directly going to forced vibration. What is forced vibration? That is what we are going to see. So whenever there is some external force applied to a system, there is an excitation on the force on the system, and which produces vibration. Then the vibration is termed as a forced vibration. So forced vibration is a system of vibration containing some excitation, a means of excitation. So, however, when the forcing frequency increase to the system natural frequency, then the amplitude of vibration will increase suddenly, and then it produces resonance. So we have discussed what the meaning of resonance at the very beginning in our introductory lecture. So it is not new for you. So as we see from here, the magnitude of amplitude is here, frequency is in this axis. So on that, we can see at the point where resonance frequency take place, that means natural frequency that divided by resonance frequency, the amplitude becomes very high, going a peak like this. This is the phenomenon of resonance here. Okay, so that is what we are going to see. Some of forced vibration case in our real world are like ringing of electric bill is one of the forced vibration case. Vibration of air compressors that produces vibration. And there are various types of forces, external force, source of external force, as well as types of forces which will be imposed to the system, like periodic force, impulsive force, random force. Periodic force means when the force is, for example, we can see this repeated type of forces. Okay, so that are called a periodic force that repeat itself after every interval of time. Within one natural frequency, it will repeat itself. So that are called periodic forces. And the force which excited or applied to the system with a kind of impulsive or propulsive kind of forces, which given at one time are called impulsive force. For example, this is impulsive force. It is linear here and dropped immediately. Applied once and dropped. Or here, these are kind of impulsive, multiple impulsive forces. So, and random kind of forces also be applied to the system that can produce vibration. So these are some type of forces. This thing is hiding. Let me put it here somewhere. So static forces. Static force means a kind of constant loading, or it is a monotonic type of loading. For example, if this is the force versus time float. So on this float, what we can see, this constant force applied. For example, this is called static force, or that is known as monotonic force. And there is also dynamic forces, which change with time. This will not change with time. As we see, At this point, it is the same. Again, here you go, it is the same. But in the case of dynamic loads, they are changed with time, so that it is called dynamic. So this dynamic forces can be taken as some of them periodic, others impulsive and random forces. And when we come to periodic forces, harmonic forces and non-harmonic forces are there. Okay, and harmonic forces can be steady state and transient. When we so in most of our next analysis and the preceding analysis, we will see this harmonic force type, including the steady state and transient analysis of vibration. Okay, so this shows us a two-dimensional float of force versus time float with various types of forces that actually act upon the structure and which produces vibration. So rapid or transient loadings is like this. There is also slow loading is like this. Again, there is sinusoidal loading kind, or cyclic or repeated loadings are there. So these are and we can see here a three-dimensional representation: displacement versus frequency, or displacement versus time flows. Here you can see displacement versus time, and this is displacement versus frequency flows. So along the displacement versus frequency axis, we can see the frequency is smaller here, and when we go here, higher frequency of oscillations we can observe, and here very high frequency of oscillations. Okay, so this is some type of representation which we can use the vibratory system, and we can represent it in terms of displacement versus time. Okay, so as the time increases, how the system will vibrate. Okay, so this is a long time axis. Another, now what are the harmonically excited vibrations? That is our main intention now, because this harmonic excitation and some non-harmonic excitation, sometimes impulsive and random excitation forces are considered. So what are these harmonic excitations? Let's see those things. In general, the equation of motion for vibratory system is expressed in terms of these parameters. These are the three elements: mass, stiffness, and the damper are the main parameters which we consider. And f of t, the harmonic force f of t, is applied on the system. So, and the system is moving this direction is taken as positive, so that is a forced vibration case. Okay, so this is the free body diagram of the system. And considering this free body diagram, we can immediately develop the equation of motion, or dynamic equation of motions. So that is mx dot plus cx dot plus kx is equal to f of t. This f of t can be any type among what we have listed above. Okay, so it is just a excitation force which produces kind of disturbance on the system. Okay, so f of t is a harmonic force. In this case, we consider, because it is harmonically excited vibration what we are talking, so harmonic force is considered. The harmonic force can be expressed in terms of sine and cos expression, as well as we can express it in terms of exponential form. For example, this is exponential form. So these forms are most common form of mathematical expressions to define various type of vibration. And here F naught is we consider some kind of amplitude of force, that the maximum amplitude of force. Okay, so if sine is 0 or sine is 90 degree, this implies f of t is equal to f naught. If cos is 0 degree, f of t is equal to f naught. So that is the meaning. Okay, so let's consider the exponential expression in our equation, substituting this part of equation on the above equation, this equation number 1. So that the results as mx dot plus cx dot plus kx is equal to f naught e the power of j omega t. So consider this as equation number 2. Now, so this is second order differential equation. So it's non-homogeneous because, as we see, it is not mx dot plus cx is plus kx is equal to 0. Then it is homogeneous. But now it is different from 0, which is different from 0. We have this component, so that it is second order differential equation of non-homogeneous type. And this type of equation needs or has two parts. When we are solving this type of equation in mathematics or in our linear differential equation, we can have two different parts. These are the complementary part, known as the transient response, and the particular solutions. We call that as a steady state response. Okay, so in complementary function, the solution is for the homogeneous part. We consider only the homogeneous part of equation, and then we find the solution. And in the case of particular or steady state response, we consider the whole system, okay, and we find a solution which satisfies the kind of the equation that at the left side of equation. Okay, so the complementary function, it is a solution for homogeneous equations that described in the previous chapter for zeta less than 1. The solution was written as sc of t is equals to we can represent, we already developed for mx dot plus cx dot plus kx is equal to 0. For such equation, we have seen various cases, solutions in the previous case. In previous lecture 1 to lecture 5. Okay, so we can refresh that part. Let me take some laser. Sorry. Okay, let me. So this part is the solutions for homogeneous system of equation, and the particular solution for the non-homogeneous equation, we see the type of equation here. What is this equation? For example, E j omega t. So we can select similar type of solution. And the x particular of time t is equals to x e, the exponential form. We selected here exponential. If this part is trigonometric or sine or cosine type of solution form, then we select sine or cosine form. And we select based on the type of representation here. Okay. So X is called the steady state response amplitude. This X bar is steady state response amplitude. So these two solutions, XC of t plus XP of t, gives the complete solution for the this equation. Yeah. This is solution for homogeneous part. Homogeneous part means this part of equation is equals to 0. And this is for the particular solution for the steady state response. So this one plus this one gives us the complete solution. So our x of t, simply x of t, the solution is equals to xc plus xp. This is what we need. So substituting those particular integral into equation number 2 and solve for x bar, we can get this equation. Means by substituting the particular solution into the main equation or the equation of motion, finally we can get this equation. And this equation represents the steady state amplitude of the vibration. This is called steady state response amplitude. So steady state response amplitude is obtained here. Okay. By writing k minus omega square n plus jcw as this expression, we can find the phase difference. Pi, here pi is the phase difference, okay? The phase angle between force and response. Response is the amplitude, and the force is the F naught. So this x, the magnitude of x is equals to, magnitude of x bar is equals to F naught over k minus omega square m square plus CW as a whole square. So this is the steady state amplitude of the motion. So therefore, the particular integrals can now be written as x particular is equal to x bar. So x bar is this value. So we can substitute this into here. This will come to here. Okay. Then that is the final solution. Sorry. So x bar and x pi may be written as like this. Okay. F naught over k, and this R represents the frequency ratio. That means omega over omega n. Okay, so natural frequency, excitation frequency over natural frequency, the ratio. So this can be represented in terms of ratios. Okay, 1 minus R square. That means omega over omega n square as a whole square plus 2 times zeta r square. And the phase angle phi is equals to tan inverse of 2 zeta r over 1 minus r square. The total solution, as I explained previously, it is the sum of xc of t plus xp, and which gives us this equation. Instead of x bar, we can put this equation, then it will be a complete equation. Now, C1 and the C2 in our homogeneous solution, C1 and the C2 are not defined. These are constants which can be defined from initial conditions as well as some prescribed conditions. So for the force form f of t f naught sine omega t x particular. This is what I have discussed at the very beginning, because for f of t type, we select this type of equation if it is given in this form. If it is given in this form, we select this form of equation. But in the previous case, we selected the exponential form, so the solution also exponential form. Means our f of t was f naught is a power of I omega t. So the final solution also select solution x particular of t is considered the same form of this form of equation, like what we have here. So the transient response of x complementary of t represents emotions that decays with time. Transient response decays with time, and can be neglected after certain times, because that is a decaying function. Okay? Steady state response x particular of t is harmonic motion, which with constant amplitude and frequency omega. Okay, so the term f naught over k is called the static deflection. Here, this implies static deflection, delta naught. Okay. Or delta S, you can take. So the ratio becomes x bar over x static is usually called magnification factor. This is, we call it as magnification factor. So magnification factor is, magnification factor is equals to 1 over 1 minus r the whole square plus under radical, 2 zeta r as a whole square. So that is magnification factor. So here we can represent the relation between amplitude ratio and the frequency ratio, as well as phase angle versus frequency ratio. Okay, so here we have if the amplitude is taken from point 1 as zeta, this float is all the functions as are represented in terms of zeta. So this point implies the point where omega over omega n is equals to 1. Okay, that means resonance point. From here to here, it is showing resonance region. From here to here, resonance region. So as we see, as zeta, the value is very less, that is 0.1, then the amplitude goes beyond the margin. And as the zeta value increase, the amplitude decrease. Okay, for zeta 0.3, it is like this. For zeta 0.4, it is like this. As zeta 0.5, we can see like this. And more zeta, this graph comes to like this. Okay, so this is deflection of the system divided by static deflection equal to 1. Means this is a point where magnification or amplitude ratio or magnification factor is equals to 1. And as magnification factor increase, we can see the condition for resonance also increase. Yeah, so this is the representation of amplitude ratio or magnification factor versus frequency ratio. And when we come to here also, this point represents omega over omega n is equals to 1. That means when they coincide, that is the point of resonance. Okay? This exactly 1 means that is exactly the point of resonance. Or when it approaches to this point, the occurrence of resonance is certain. Okay, so and here also phase angle from 0 to 180. Okay, so what's going on here? For smaller value of zeta, for example, if zeta is equal to 0, we can see a straight line like this. Okay, and for zeta, here also like that. For zeta increasing from 0 to some value, we can see this float. The float goes like this. Okay, for zeta 0.25, it is like this. Again, zeta 0.5, it go like this. And zeta is equals to 1, it is. These are the representation of magnification factor and the phase angle zeta, phase angle pi. Downward force vibration system. So for zeta is equal to 0, the system is reduced and become undamped. For any amount of zeta greater than 0, the amplitude of vibration decreases. That means to control the amplitude, we must introduce some kind of damping. Unless and otherwise, it will go to unlimited condition and results in the resonance. And the resonance is undesirable condition in our discussion, in our previous discussion. So for the case of R is equal to 0, the magnification factor is equals to 1. The amplitude of the force of vibration approaches 0 when the frequency ratio R approaches the infinity. As M approaches to infinity and R approaches to M approaches to 0 means R approaches to infinity. For zeta 0, the phase angle is 0. For 0 to less than R or less than 1, R means here it is the ratio omega over omega n value, and 184 R greater than 1. Okay. For any amount of zeta greater than 0 and 0 less than R or less than 1, 0 degree less than pi, pi less than 90 degree. That is the conditions. For zeta greater than 0 and R greater than, this all explains about the condition here. Okay. Yeah. So variation of displacement with frequency. Okay. We have this equation, and this implies the static deflection. Okay. Okay, so is the solution for response of amplitude. Okay. At low frequency means R approaches to 0. Then X approximately equal, because if this is 0, 1 square is 1 plus and this is again 0, means this part also taken out. So F naught over K over 1 means it is F naught over K. Okay, which means the displacement is stiffness control. Okay, we control the stiffness of the material in order to control the displacement. Okay. At high frequency, that means R is too much greater than 1, then X bar is equal to F naught over M omega square. Means what? If this is very high, that means this can be controlled by mass. From this equation, we see mass can control the displacement. Okay, so the amplitude of displacement can be controlled by mass. Again, at resonance, that is R is equals to 1. R is equal to 1 means this component is 0, and this component is 2 pi, that means 4 zeta square. So F naught over 4 zeta k. 2 zeta k. It is under, actually, it is under radical, so that we have 2 zeta only. So F naught over 2 zeta k, which means displacement is damping controlled. In this case, it is damping controlled. Okay. So these are the 3 methods of controlling how we can control the excessive amplitude in various cases under low frequency, under high frequency, under resonance frequency condition, how we can control. So in resonance damping control, at higher frequency mass control, at lower frequency stiffness control is required. Frequency of maximum amplitude. Okay, the X bar is equal to F naught k over this phenomenon. This is under radical, so it is minus 1 over 2 implies radical. So X is maximum when D over dr of X naught is equal to 0. This is the minimum maximum mathematical approach of finding minimum or maximum. So X bar is this magnitude of X bar is maximum when D is equal to D dr of X bar is equal to 0. Okay, when this is satisfied, that is the maximum condition. This condition gives X is maximum when R is equal to omega over omega n, which is equal to 1 minus 2 zeta square, which is known as resonance frequency. So omega resonance, sorry. So omega resonance is equals to omega n times 1 minus zeta 2 zeta square under radical. So this is a resonance frequency. Okay, so forced vibration due to rotating unbalance. Let's see some physical approach of considering forced vibration. So as we see here, rotating unbalance is there. This is a rotating machine, and there is a small eccentric mass is here with M, representation M. And whenever this machine is rotating, this eccentricity produces unbalance in the rotation. Okay, not eccentricity, but the unbalance in the mass at that point. Okay, kind of jerking or a kind of unnecessary noise also be produced because of the presence of this mass. Okay, so unbalance in the rotating machine is a common source of vibration excitation. If MT is the total mass of the system, consider capital MT, as total mass of the system. And m is a centric mass. Here, a small centric mass m is there. Okay, centric mass. And omega is the speed of rotation of the machine. Then the centrifugal force due to the unbalanced mass is me omega square. So it produces centrifugal force. It pulls out the system outward. That's called the centrifugal force. Okay, where E is the centricity here. This is the centricity or the radius of centricity. The vertical component of me omega square sine omega t. So we can resolve the vertical and the horizontal component of this mass. So the vertical component is me omega square sine omega t. Okay, the horizontal component me omega square cos omega t. Okay, is actually the vertical component is the effective one because it is in the direction of motion of the system, and that the equation that govern will take this form: mt x dot dot plus cx dot plus kx, which is equal to me omega square sine omega t. So this is a general equation for this system, because we have here stiffness, we have here dashpot, we have here general mass mt. I can call it mt here, and the small mass m is here, which produces the centricity, or which produces centrifugal force. So this is a general equation for this type of represent, or this type of motion. So for this, me omega square over k, because the force F naught is, this is F naught. Okay. Here we call this part as kind F naught, according to our representation, this part F naught. Okay. So instead of F naught me omega square over k over radical of 1 minus r square as whole square plus 2 zeta r as whole square. And rearranging this thing, finally, what you can get, me over mt, the total mass, times r square over this thing. Okay, so means after finding solution for x bar, this is, and the phase angle is represented like this. So the plot of this x and phi are shown in the figure below. Yeah, this is actually, no, I didn't plot this thing. It is already, as we have discussed in the previous case only, because we discussed similar approach here. Yeah. If the deflection of foundation is negligible, then the force transmitted to the foundation is F eig omega t, which is equal to kx plus cx. So it goes, this is foundation actually here. This is foundation. So if we cut this, okay, the free body diagram becomes, the free body diagram gives us kx plus cx, which is, if that is transmissible, the force transmitting to the ground. Now what we are talking is transmissibility of the force. Okay? So if we cut this system here and consider that is kx, again there is C x dot so transmissible force, the same thing happen here. F transmissible. So that can be taken as F transmissibility in the exponential form. Okay, that transmissible force can be represented like this. Okay, let's see this. Okay, so yeah. Then, assuming harmonic motion, then x is equals to xe I omega, because this is the same form we select. So for that, finally we can get f transmissible is equals to k minus j omega c times f naught over k minus omega square m plus j omega c. This is called force transmissibility. We call this as TR F, which is equals to force transmissibility, which is equal to F transmissible over F naught. So F transmissible over F naught gives us transmissibility, force transmissibility, which is equals to 1 radical of 1 plus 2 zeta r square over 1 minus r square plus 2 zeta r the whole square. This is the force transmissibility. Actually, we have displacement transmissibility and force the transmissibility. We can see what displacement transmissibility later. So the phase angle pi is equal to tan inverse of 2 zeta r over 1 minus r square. The forcing function for the base excitation. Now this is the case of base excitation or displacement transmissibility. Look, there is a base, there is a mass, and there are supporting structures. So the base is considered as giving kind of sinusoidal motion. So how that motion transmits to the machine, from base to machine. So consider the sine type of motion of the base. Okay, so take the free body diagram here. K minus x minus y, because y is resulted from here. Base is also giving an input. C is equal to x dot minus y dot. Because now the equation becomes mx dot plus c minus x dot minus y dot plus k times x minus y. This is actually we can observe the seismography in the that measure the earthquake. The amount of earthquake can be measured in this type of analysis. Okay, so this is the form of that. So substituting the forcing function into the model, what you can get, because here y is equals to y of t is equal to y sine omega t. So y dot is equals to y omega cos omega t. So we substitute those things. Okay, instead of x, instead of y, we substitute them, and finally we can get let's define it as a sine omega t minus alpha. Okay, so where a is equals to y or radical k square minus c w square, and alpha is equals to tan inverse of minus of c w over k. So define this, and or finally assuming the solution x of t is equal to x sine omega t, because here a sine, this means the solution becomes x sine omega t, harmonic motion. Okay, so displacement transmissibility here is Tr of d is equals to x over y. There, the force transmissibility is equals to F naught over F. Here, F transmissible divided by F naught is the force transmissibility, but here x over y is the displacement transmissibility, so which is equal to k square plus cw square divided by k minus m omega square as whole square plus cw square, and which is in terms of zeta, we can represent it like this. When phi is equal to tan inverse of 2 zeta r over 1 minus gamma r square. Yeah, so this is the displacement transmissibility versus frequency ratio. As we have discussed previously, as zeta very small, the amplitude becomes very high and goes to resonance. Okay. For higher and higher damping, we can get an appropriate type of amplitude. Okay. Yeah, this is the graph. And this is also the phase angle versus frequency ratio graph for various values of the damping zeta. Another second example with some numerical value, just substituting some numerical value. Let's consider reciprocating pump having a weight of 68 kilograms is mounted at the middle of steel plate. This is a steel plate of 250 centimeter with 1 centimeter thickness, and the weight is 500 millimeter or 50 centimeter widths. And so having some widths like this, 50 centimeter widths. So this is mounted on this plate, and the plate is fixed at both sides. See, it is fixed here, and which is clamped along 2 inches as shown on the figure. So during the operation of the pump, the plate is subjected to harmonic force F of T is equal to 220 cos 62.832 T Newton. And the youngest modulus of material of the plate is given 200 gigapascal, and required to find the amplitude of vibration of the plate. So find the amplitude of vibration of the plate. So there is a reciprocating pump here, and this is the frame. There is a piston cylinder mechanism here, okay, and having a connecting rod. So it rotates like this. The rotation of this about this center produces the translational motion of this thing, like this. This is the rotation of this produces translational motion of the, here there is a translational motion. So that is what. So the plates can be modeled as a fixed beam from the concept of strengths of material. So from the strengths of material, we have a beam which is fixed at both ends and subjected to kind of central loading. We have K is equals to 192 EI over L squared. Here E is the youngest modulus of material, and I is the material that is given as 1 over 2 BHQ. Okay, and L is the length, so 192 EI over LQ. So all are material properties. and geometric properties. So we define them. So I is defined as finally we can get 41.667 times 10 to the power minus 9 meter to the power of 4. And K is obtained from this relation. So the maximum amplitude X is found as F naught, X is equal to F naught over K minus M omega squared. Okay. So from this, we directly substitute the values of these constants, and finally we get minus 1.32487 millimeter. So showing that the minus sign shows the response is out of phase with excitation. Okay, so this is the value. Example 2. Find the total response of single degree of freedom system with mass 10 kg. Damping constant is equal to 200 Newton per second per meter. K is equal to 4,000 Newton per meter. And the initial condition X naught is equal to 0.01 meter, and X naught is equal to 0. When an external force F of t is equals to this type acts on the system with F naught is equal to this omega this. Okay. This also is already defined. 100 cos 100 cos 20. So from the given data, omega n is equal to k over n. So immediately omega n is found as 200 rad per second. And zeta is equal to c over 2m omega n. So zeta is 0.05. That is lower zeta value. And the damped frequency of the system is 1 minus zeta squared, the radical times omega n. So which gives us, this is the damped frequency. And frequency ratio, omega divided by omega n. So omega is given 10, and omega is 20, omega n is 20, so which is equals to 0.5. So all parameters are defined. And this static deflection, delta S is equal to F naught over K. So this is the static deflection. So X bar is equal to static deflection divided by radical of y minus r squared as a whole square plus 2 zeta r squared, which gives us 0.3326 meters. Okay, this is X bar, magnitude of X bar. And the phase angle tan inverse of 2 zeta r divided by 1 minus r squared, which gives 3.814 degree. So the solution x of t is equal to the complementary solution x of c of t plus x of particular solution of t. So x of t is equal to ae the power minus zeta omega n t cos omega n t minus psi plus x bar cos omega t minus 0.066. Okay, finally, we can find the solution x of t. This is the solution. At t is equals to 0, x of t is equal to 0.0. So we can we have those points. Means initial conditions are already given. Okay. Means x of t, x naught is equals to 0.01 meter. Means at x at t is equal to 0, x of t is equal to this. That means we substitute this value here. Immediately we can get a cosine because we have some constants which should be determined here. this A must be determined. Okay, so that can be from initial condition. So A cos psi is equals to minus of minus 0.33187. Again, if x of t is this, we find x dot of t. So this is x dot of t from this. Means which is dx over dt. Dx over dt is equals to x dot of t. Means we have given v naught of t is equals to 0. So substitute that initial condition at t is equal to 0, x dot of t is equal to 0. So when substituting, we get a sine psi is equals to this. So now we have two unknowns. One is the psi, and another one is a. So substituting these values on the equation, we immediately get the values of psi and the equation. This is the general equation of motion. Okay, psi is equal to 0.066 rad, A is equal to minus 0.3325. So this is the solution. So thank you very much for watching this. Okay, this is all about for today.